There are two types of equilibrium problems that involving calculations of the key C, key P and the quantities of the species at equilibrium. The first problem is when the equilibrium concentration and pressure is given. We need to find either key C or Kp or both. We will using the expressions or the formula of Kp equals to Kc RT delta N to solve it. The second problem is when the initial concentration or pressure together with the Kc or Kp are given in the question, and we need to solve for the equilibrium quantities. In order to do this, we need to use ICE table. There are three steps on using ICE table. First step, express equilibrium concentrations or pressure of all species in terms of the initial concentrations or pressure. Express a single unknown x, which represent the change in concentration or pressure. Step 2. Write the equilibrium constant expression in terms of the equilibrium concentration Kc or pressure Kp. By knowing the value of the equilibrium constant, we can solve for the x. The third one, having solved for x, finally, we can calculate the equilibrium concentration of all the species. Dissociation reaction of PCl5 is when this molecule broken down into a smaller molecule of PCl3 and Cl2. From this equation, we can find the fraction or the percentage of molecule that dissociate, or known as degree of dissociation, with a symbol of alpha. The value will be equal to 100% as percentage or 1 in a fraction if the dissociation occurs completely. But if incomplete dissociation occurs, this formula of alpha need to be applied either using a value of concentration or pressure. Reaction quotient is the calculation involving substituting the initial value into the Kc or Kp expression. Since here we have the Kc, so for the reaction quotient we will have a Qc, the same expression as Kc but differ in the insertion value of the concentration. For the Kc, the concentration value is at equilibrium, and for the Qc, the value of concentration is at initial. By comparing these two values of Kc and Qc, we can determine whether the reaction has reached equilibrium or not, and also predict the direction in order to reach equilibrium. If K has the higher value than Q, it shows that the system is not at equilibrium. The lower value of Q indicate that the concentration of product is lower and the concentration of reactant is higher. In order to reach equilibrium, the reactants must be decreased and products must be increased. Thus, the system will proceed to the right until Q equals to K. If the value of K is lesser than Q, it shows that the system is not at equilibrium. The higher value of Q indicate that the concentration for both product is higher and the concentration for both reactant is lower. In order to reach again the equilibrium, the reactants must be increased and products must be decreased. Thus, the reaction will proceed to the left until Q equals to K. If K and Q have equal value, this indicates that the system is at equilibrium. Thus, there is no further net change occur